Hopefully, there are people for the yeah, sure. Okay, yeah. Welcome everyone. Let me introduce our speaker, Dominik from MPI Munich, and we'll talk about quantum corrections for ourselves.
Yeah. Hi everyone, thanks for the nice introduction and thanks again for having me. So, yeah, today I'll be talking about quantum corrections on the running of the field space geometry. The talk will be mainly based on our recent work, the archive, with great collaborators, Haslehner, Luigi Fronte, Emanuele Gendi, and the supervisor, Divaila. And to spoil you right out the gate, you need a main point variable base. So, what I want to get to is that the curvature of the field space manifold changes as a function of the renormalisation scale. Curvature of the field space manifold, we're just going to call M. Changes as a function of the renormalisation scale E. Yeah, so what we will see is we have the curvature depends of our field space manifold given by R A B C D. And we include quantum corrections and counterterms. We will go on to the expression of geometry-kinematics and the renormalization scale mu. So schematically, let's just do it. We have our field space manifold given by a sphere with a radius r. That's 3 levels. If we go to loop level, radius will change. Now also the function of scattering kinematics and the renormalization here. Hope my handwriting is readable enough. If you need more, if you want it bigger or small, you can just say. So very small. Yeah. Right. Okay. So from this point, so
you don't have to renormalize it yet. The scale.
Good one, yeah. So, okay, to get to this point, I will go through it step by step. So, first of all, I'm going to do the introduction / recap to the what we call the field space geometry, where I will show you or convince you that the invariance on the field space and the field redefinitions of quantum field theory can be interpreted as the invariance of the manifold on the coordinate change. And we'll try to, or I will show the physical observables are given as or by a geometric variance of field space manifold. And I'm going to go through this exercise on the nonlinear linear model. Then we're going to be doing loop corrections. So we go to one loop to the NLSM, focusing on the all-in 4-point amplitude, which you can derive by on-felt methods or Feynman rules. Here I will try to convince you that this one loop amplitude has a universal structure. Structure and curvature tensor contractions. And then we will introduce a counterterm and try to renormalize the theory, which will already take us out of our nice metric framework. Then to fix this, I'm going to be a brief interlude and introduction to the geometry kinematics duality, which was introduced by Liv Chung, and Julio Martinez in 2022. I'll give a quick introduction to this framework and show it's why it's very useful in our particular case, so we can give the counterterm a geometric explanation in the NLSM. And finally, we're going to come to what I call overview of the curvature, renormalization, where in this section we apply the duality to see how the curvature runs. We're going to again work on the NLSM. we're gonna employ the universal counterterm structure. That are multivariate, where here we have symmetrization. And the symmetrization, Riemann tensor going on. And we will finally see the statement about curvature and now become the function of the renormalization field.
Sorry, what is the subscript on the A4, the 4-point function? It's CL.
Sorry?
Superscript.
Yeah, one loop.
One loop. Oh, one loop.
Yeah, basically, cannot read, just yeah, I'm used to criticism of my handwriting.
All right. And we have to log off, I'll give a quick upload / recap what we have done, or what still can be done. Okay, now let's start back in to one, the field geometry. Okay, I want to explain this on a massless derivative interacting scalar theory. Scalar theory with no potential. So basically what I want to talk about is the nonlinear sigma model. So let me write down the local function as 1/2 where GAP I just delta functions net term. So much for linear phi, this is for quadratic phi, and so on. So this is just so far it's just a polynomial in phi that allows me to neatly collect out all the two derivative interactions of the theory. Now we know that quantum field theory is field redefinition invariant.
Sorry, Dominik, what characters the indices in the phi and phi squared terms and
Yeah, I will write this more explicitly, but it will be something like here we have a coupling, frequent coupling number A and C by C plus 4-point coupling CD for CD phi D.
and this lowercase uppercase lambdas are constant tensors, or they will be
They're like they're coupling constants, so they will constant tensors in this case. And we will see how to give them geometric meaning. Yeah, thanks for it. Okay, so we know QFT is field redefinition invariant, meaning that the physical S matrix is independent of the interpolating fields. Invariant. So if I draw here the set of all possible field redefinitions we can do, that leave our S matrix invariant. I want to be instead of focusing here on a subset of field redefinitions on the which or field prime A, that's the field prime tilde of A, where tilde of A is just a function of the field phi, and not a function of the field phi, the derivatives of field phi and higher stuff. Okay. Why do I want to look at the special field redefinition?
Can you remind me So when people say it's field redefinition under the, when there's a derivative in the transformation, then it's more subtle, right?
It's more.
It's more subtle.
Yeah, I mean, it works. You can do.
You claim it works.
Yeah, it's field redefinition invariant under everything you can do, right?
Okay.
If you.
Local field definition.
Yeah, you can even go to non-local. There was a recent paper by Tim Cohen and Andreas Helset, where they claim that you can also do something crazy, like you can go pi to 1 plus, I don't know, 1 over plus pi. And this also works, and you see the non-localities canceling out in the primary diagrams. So, yeah,
But there's of course a difference between examples and then it works always.
yeah, I mean, they've proven this.
They prove it in that example.
No, they've proven that you can do non-local field redefinitions.
Of any kind or of a particular kind?
Yeah, pretty much any kind. I mean, they have proven it explicitly for scalar theory,
Oh,
and they argue that generalization fermions and other stuff. So,
I think the statement is that as long as the field definitions do not change the LSA conditions, you do not change the vacuum and you do not change the one particular function such that it cannot be captured by a function renormalization, such transformations will always work. Doesn't matter if it's local or not. Because it will always change the S matrix, keep it unlinear.
yeah, I think they have a statement about what happens when you change this set. So then your LS set formalism also has to be adapted to it. But yeah, okay, so they say, or they claim in their paper, that you can do whatever you want in the non-local. But here we're going to be simpler, we're going to stick local, and I want to drop the derivative for even for simplicity. So technically we could do everything, but I just want to focus on these field redefinitions here, where phi just goes to a functional phi. Does that answer the question?
Yes.
So why these field redefinitions now? Because now we can look at what kind of tensor structures emerge under these field redefinitions. So let me first consider the space-time derivative of the field phi A. We form the field redefinition of this subset. So now we have d phi tilde A, and by application of the chain rule, we can write d phi tilde A. So d by tilde A by b mu b. Okay. So this already reminds us of the transformation of the transformation of a vector. Of a vector on a manifold M, where phi A itself are coordinates. Now we can look at now under this subset of field redefinitions, what happens to our GAB? So under the special subset of transformations, GAB I goes to B AE tilde I tilde, which is just given as d phi c d phi tilde b d phi tilde b c d of phi. So here we see GAB transforms like 0 2 tensor. From our definition of Lagrange, we see GAB is symmetric, it's a bit contracting into some with the symmetric quadratic term, and it's called it's definite. Otherwise, we have ghost state in the theory. It's non-degenerate. So possible what's called the duck test. If it looks like a duck, swims like a duck, and talks like a duck, it's probably a duck. So since it has all the right properties, let's just call VAB of phi a metric. Because it just forms like a metric and design it is symmetric. So what have we done so far now? We have given our theory. We've given the NLSM and the structure of the Riemannian manifold. Riemannian manifold M, where fields by A are coordinates. Du by A are tangent vectors. And the A phi, what we call it the field space method. So you're very cartoonish picture. Here, for example, we have our manifold, where here is the coordinate line by 1, by 2. Up here at the origin, we have a tangent space where D by 2, D by 1 live, and on this manifold and field space manifold, we also have our metric structure given by this. Okay, now you can ask, is this actually useful, or is it just a trick of rewriting something and forcing some structure on it? We try to convince you it's actually useful. So what do you usually use this from here? Clean or
Well, if it wet, then dry.
wet?
Then you don't use it. Should I get mine?
Oh,
But isn't that the dirty one? It's the
Yeah.
When it's black, it's because it's used on the whiteboard.
It does have some bits. So this is normal for the
Yeah.
whiteboard, no?
In the meantime, Dominik, can I maybe ask a question? Yeah. Is anything known about the topology of the subspace for which the field definitions are only derivative? Like whether it's an open subset of all possible field definitions or.
okay, to be honest, I don't know if this has been looked into that. I mean, the idea now is to just focus on this subset. Should this subset be create a field space manifold? Then we convince ourselves that on-scale amplitudes are always given this geometric invariance, and then we can say this works for all, should work for.
Yeah, but I mean, I know that some people who have looked into the derivative field definitions as well, right? Like Amish and.
Yeah, so it's clearly not an open subset in the bigger space, right? I mean, it must be very restricted, sort of closed subset.
Yeah, I think that what is the boundary? Right?
Yeah.
If it's not open, then what's the short boundary of the it's.
Right. In the same way, I'm wondering, I mean, if I really have to do some non-local transformation, and then I will get some very ugly Jacobian in the past, so after doing this part, change of coordinates, and I would have big trouble in giving meaning to this functional determinant.
I mean, you can do this the way the Cohen and do this in their paper is you can bring it up into the Lagrangian as ghosts.
I see.
So like this study.
Yeah, but then again, that's typically done in a local for local field theories.
Yeah, but I mean,
Non-local
you would start with a local theory, right? Then you do your ugly non-local transformation, but it still has to describe the same theory. And you can convince yourself if you draw the diagrams that the ghosts will always cancel out and you won't turn out the teeth.
Yeah, but I guess I guess if you really honestly have to give both formulations, I think it would be difficult to rigorously claim that it's the same, or maybe even define in some cases.
Yeah, well, it's almost by definition.
Yeah.
Yeah.
Yeah,
That's
but
why
then it's just,
Yeah.
I mean, then there's almost no statement, right? I mean,
You have to take the
Yeah.
different, I guess.
if the definition is, oh, I always have to go back where I know what it
Well,
means.
I mean, they're probably already where you can check it, but.
Yeah.
The generality, I don't know.
Yes, I mean, I can highly recommend the paper, they show it on. At least
Yeah, but scalar calculus, I think the paper is very. So
Dominik, can you push up the other one? Thanks.
Sorry. I mean, if you have further questions, just go ahead and ask. Okay, so if not, yeah. It's just a very rhetorical question. Is this useful now or just a nice trick? The answer is yes, it's actually useful. As we'll see now, when we compute the on-channel amplitudes, which we know are invariant under field definitions. So what now for like the next 2 minutes is just a claim that on-channel amplitudes depend only on the geometric invariance. And only on the geometric invariance of the field space manifold, so stuff like the Riemann tensor, covariant derivatives of the Riemann tensor, and so on. Of the field space manifold. Okay, to make this more explicit, we have now manifold with a metric. We know where we at least, I think we have all of us have at least some intuition of GR and a bit differential geometry. So we know that, let me just, so we know how to handle stuff with metric. So now we have our field space metric GAB of phi. Then we do a Taylor expansion of it, about the origin, or about the vacuum configuration of the field phi, which I can choose to match at the origin. So we have DCGA E at the origin of phi half second derivative DCGD and D from the 0 and C by D plus higher order terms. Now, what I meant with our geometrization, we know that there exists a very special coordinate system, the Riemann mode coordinates, in which, first of all, the stop symbols, C, origin, vanish. So the covariant derivative at the origin, the partial derivative. Also, we know in Riemann mode coordinates, second derivative of the metric at the origin is related to the symmetrization of the Riemann tensor. So now what we can claim is that the Lagrange, we can go, we have a manifold, we know manifolds are invariant on the coordinate change, so we change the coordinates in our matrix, so we have 1/2 AD plus 1/3 our AC AC G plus 1/6 E or AC.
There seems to be a B index missing from your curvature.
the last E should be B. On the right hand side of 2/3 of our.
Yeah. Thanks. Very good eyes. I E A B. Okay, so now the ground already looks a bit simpler.
Can I ask a question? I probably should have asked it at the start. why don't you call this a target space? Because kind of acts like a target space, right? A little bit.
Sorry, what do you mean acts like a target space?
The field space,
Yeah.
you kind of treat it like a coordinate, and
Yeah, exactly.
so this is very similar to the treatment of a target space in string theory. So why would
Yeah.
The scattering amplitude of the what you call a Walsh component field, not what you are interested in electricity.
I see?
Interested in target space, space matrix is interested in the Walsh space.
I see. Okay.
Maybe it's not gonna be a target space if you take something else than a scalar field. Like, this is a sigma model, so we're very used to sigma models with target spaces, but
Yeah, that's why, because
then
the-
we're taking you are able to do this for other fields also.
I see.
So then that interpretation is not there anymore. So
Okay.
And it is not specified any dimension, like
Mhm.
this can work in dimensions.
yeah,
Yeah, but it is the target.
sigma models are also in general range.
Okay. Thank you.
Yeah, maybe later you can tell me more about this target space.
Okay.
Okay, so now we've gone to Riemann normal coordinates that are already looked a bit simpler. But interesting observation now, we started with 3-point interaction. This one doesn't have 3-point interaction anymore. But since we can convince ourselves, since we can relate them by some field definitions, it's okay. For example, if you look at the 4-point on-shell amplitude, we see it doesn't have a propagator-like pole, so we see it's actually the same theory. Now, what we achieved so far, what we've done so far is we've given our Lagrangian the structure from the infinite field space, the structure of the Riemannian manifold. Our Riemannian manifold yields by A with the coordinates. Given with some Riemannian structure with the metric, curvature tensor, and covariant derivatives thereof. And what we observe now under this subset of field redefinitions that are marked above, the form of the Lagrangian also stays invariant. Now we can sit down and compute the on-shell scattering amplitudes. We really see why it's useful. So on-shell amplitudes. We can do this by either Feynman rules or the modern on-shell approach. We have 4-point amplitude on-shell in the CD. It's given as R, A, B, C, D, T, plus R, A, C, B, D, F. 5.1 from amplitude A, B, C, D, E, given as covariant derivative of the Riemann tensor A, B, G, E, squared. Plus some permutations of the indices and generalizing on some variables. Okay, so what we see from this now is that the on-shell amplitudes indeed only depend on functions of three-metric invariance, like the curvature and its covariant derivative. This is respected since the physical isomatrix is the field definition invariant.
Is it three level also?
Yes, this is 3 levels so far. Now we see that in some sense the geometry of the field space manifold M determines the interactions. So I mean, if it were flat field space manifold, we would have no interactions, we would have free theory, so the known flatness is what gives interactions. And The other elements are ordered independently. What we use now is this Lagrange and Riemann normal coordinates to derive this, but we could have also used this Lagrange here. Still with the metrically derivatives in it, completely quickly set everything on shell, and you will see that EG and EDG would combine in such a way that we can again find the Riemann curvature tensor. Another nice observation we can already make here will come in handy. Go to loop. There is a universal structure to the Feynman rules. Feynman rules. So what I mean by this is we write down the Feynman rule, Feynman amplitude for a 4-point function. See if it comes from here. So what we expect already is that it will be some sum over the 3 factors depending from beta of the rotations of the indices of the Riemann tensor. So 4 indices. We have 24 possibilities, but we have antisymmetry in the first. So down to 12, antisymmetry in the last, down to 6, pairwise exchange symmetry down to 3, and we have the Bianco identity. So we can write this as a symmetry. So we can write this as a linear combination of 2 Riemann tensors. Antisymmetrized or a B. So final vertices in this theory are this type of universal structure where the AS and AA are now a function of the external off-color momentum, called TI scattering. And AS and AA can be even or odd the exchange of these momenta, because the momenta have to be exchanged in conjunction with the indices. Okay. So that was 3 level of discussion. Then go to 1 loop. So the 1 loop, and see how already here we drop out of this geometric framework that we've built. So due to the universal structure of this Feynman rule, we can also anticipate a universal structure of the 1 loop amplitude. And you get the 1 loop amplitude by simply doing together these 2 3-level Feynman diagrams and find the universal form of a 1 loop is going to be given like the momentum integral, a symmetric as a function of the participating momenta, a symmetrized, and then a antisymmetrized or E times symmetrized or C, then D is the antisymmetrized or C. Okay, so this is the universal structure we expect for 1 loop amplitude.
Some factorization, I guess.
Sorry?
So some factorization from level.
Yeah, it's just 2 and 3 level Feynman diagrams glued together by this index interaction. I mean, I haven't been careful about going over variant, but Yeah, and also very nice to see this dimensional framework that we perform our unitarity platform. Once it's able to solve like this. And quite nicely, only the signal model is just reduced from this and this. Okay. So now we can. Okay, so we find one loop. The same amplitude given by one group. This given by half. Mark the symmetry and the RC E X squared is 1/3. B R. D as U. All of that times the estimable bubble integral. As the process of metric terms in T and U. Okay, so here again, we see from the universal structure, we have some S squared times the symmetric combination. And we have some minus U. Times the end of the symmetrized contraction. And as we know, the estimable bubble integral, which is just given as d on K, Rho 1 more 1 K squared E squared. We'll exhibit the one right side of the divergence for some non-divergent stuff. We know how to deal with that, but get rid of the divergence, which is the usual renormalisation procedure in Q of T. So we get rid of this. We have a counter term that is able to absorb the divergence. So now we have now of the A plus 1/3 A C B on C on D on A D on B. Now we have the higher dimensional operator that can absorb the divergence 1/8 G A B C D at E maybe C D. Okay, but now we have a problem because we cannot absorb this counter term without the mass definition of the metric. See how, to just see how the ordinary amplitude now changes to S1, A, C, B, D, C, or A, B, D plus 1/4 S 3D 3D T square G B C mu square G A C B. Now, as I said, the counter term already takes us beyond our nice metric interpretation. For the action does not fit. Now, in the of the field space metric, which is just a function of phi. So the idea now would be, can we absorb this counter term into our field space metric so that it's a function of phi? Phi, or equivalently a function of the lambda. And the answer to that is yes. We can do this by deploying the geometry kinematics duality, which I give it a brief including now or a brief introduction. Yes. Um, so why should we consider this theory, or why is it interesting? I do it because by considering the theory, this will allow us to deal with derivative interactions, such as the one we dealing with now, our counter-term interaction. It will allow us to deal with more general user definitions that apply below A now be a function of phi, E phi, arbitrary derivatives thereof. But with duality, we can deal with non-tensorial interactions, stuff like mu phi A. We can deal with theories that have potential. And continuing on, this theory will allow us to deal with arbitrary massless bosons. So not just fields phi, but also scalar fields phi, but also vectors, A mu, and from radical field E. Okay, so this is why this duality is interesting. And we'll give you a brief introduction of how it works, how we can use it in our case.
Can you push up the other one a little bit higher?
Yes.
One question,
Yes.
like, what does it mean if you have a case of, like, let's say this space being flat, then you're saying all functional features are basically zero,
Yes.
and, can you remind me, like, for free theory, like multiple, like, let's say phi scale gives free theory, that is the amplitude functional zero?
Yeah.
Yes.
Okay, so, okay.
I mean, you just have
Okay, yeah, yeah.
1 to 1, right?
Yeah,
So we could-
yeah.
That's any questions, just all of that. Okay, I mean, if not, let me sketch a core idea. Inspiration, why this works, I think most, okay, I think people have heard of the colour-kinematics duality.
I'm sorry, one question. The potential is of any kind, or is there any specific, the potential for phi?
Yeah.
Is it of any kind, or like polynomial, exponential, or?
I mean, I've explicitly checked polynomial, but I mean, I think it should. One could try if it works exponential too.
Okay.
I mean, definitely works for polynomial, they claim it works for arbitrary potentials.
I see. Okay.
Yeah, fair question, yeah. But I mean, you can take your exponential, right, and tailor it to case of small field values.
Mhm.
Okay, so what this is, geometry-kinematics duality is inspired by is by colour-kinematics. Duality, where we have a gauge field amplitude here. Amplitude is given as sum over final diagrams, where we have color piece times a kinematic piece divided by a propagator piece, where the color obeys a Jacobi identity, color I plus color J equals color I. Okay, now we can rewrite these amplitudes in a form where the kinematic piece also obeys the same Jacobi identity as Jacobi identity. And now the statement or the claim of this duality is that if you take color now and replace it like in mathematics, we have then some of our final dimensions information di. This would be a PR amplitude, and in that sense, GR is given us something like Daniel squared. Okay, so this is basically the inspiration for the color-kinematics duality, where this one now works as follows. So geometry. So the idea is we take geometry and we replace it with kinematics. Specifically, how this works is we take a 4-point on-shell NLSM amplitude, B, which is given as R, A, B, C, D, P plus R, A, C, D, D, S. And now we replace the geometric Riemann tensor with a kinematic. This looks like R, A, B, C, D, as a function of P1, P2, P3, 4T, yes. R, A, C, D, D, P1, P3, 2, 4. S, the claim now is, so we start with the NLSM, we replace the ordinary geometric curvature tensor we know of with a kinematic tensor, and we can obtain other legal on-shell amplitudes. So let me maybe give you some nice examples. For example, if you want to consider a colorless by-to-the-4 theory, our Riemann is given between 3, 4, is just lambda over 3 minus 1 over u. We perform this replacement, we take the NLSM on-shell amplitude, we plug in that Riemann tensor in here, and we find the on-shell 4-point amplitude is given by lambda, as we expect for a by-to-the-4 theory. It also works for non-Goldstone theory. Where now the Riemann tensor in this theory is given by lambda p minus u. And that's again, we find the correct on-shell amplitude, lambda over 4 s squared plus t squared u squared. This also works for high derivative theory and the generic form form R will always have to be given as something like t to the row minus u of the row, because the kinematic Riemann tensor are A, B, C, D, 1, 2, 3, 4, has to obey same symmetries. Same symmetries as our familiar Riemann tensor A, B, C, D for this replacement to work. So this means that this is minus B, A, C, D, P2, P1, P3, P4. So here we have antisymmetry in the first, also antisymmetry in the second, so we have a pairwise exchange, and this kinematic Riemann tensor also has to obey the Bianchi identity. Okay. So how can we get this?
What do you think of the Bianchi identity is?
Sorry?
So you mean the first Bianchi identity?
I mean, what I mean is A, B, C, D, plus R, A, C,
Ah, yeah, okay.
R, A, B, C,
This is, yeah.
is 0.
That's the first.
Yeah, that's the first. Exactly. So has to obey the same symmetries, and then has to obey the first Bianchi identity. And as I said, you cannot think as A and P1 as separate. So you have to do exchange in conjunction. Same here. Okay, so how do we get this? How do we get this kinematic Riemann tensor? So the way that this works is we have the Lagrangian of our theories. Then we want to consider the action of the space-time integral of the Lagrangian. And then we Fourier transform the fields to be in momentum space. So the action will look like the action. I'm writing it in this form, and this is what's going to define us, our curvature tensor. Here we just have an integral over P1, P2. Move on to P2 from the kinematic term, from the, still have it somewhere. Okay, from the field space derivative, space time derivatives there, P of by A on P1, by B of P2. Okay, we bracket delta AB, and I can insert the delta function from the Fourier transformation plus integral over P3, G, A, B, C, function of P1, P2, P3, delta 1, 2, 3. That's 1/2. 4, B, A, B, C, D, G2, B3, B4, C, B, C, and momentum conserving delta function and higher order terms. Okay, so take the Lagrangian theory I have, or I want to describe, Fourier transform it, write it in this form, and then I can just read off the metric coefficients. First one is canonically normalized. Here I can read off the first derivative. Here I can read off a second derivative.
Are you using the notation that stroke length is LCGAB or another momentum space version?
So,
I mean, momentum space version of that. Is that it?
yeah. Okay. So basically what I mean is, let me just write this one here, and then I'll get back to this. So here we have our field space metric AB that we know of, and we can go here and we replace it by the momentum dependent version with the delta function. On here we were saying that the GAB, the first derivative, this is going to AB square C. 1, 2, 3, 1, 2, 3, and same with higher stuff. What I mean with the stroke now here is, yeah, okay, this comes from the first derivative of the metric, but in here you have to enforce the symmetry in 3 and 4, and symmetry in 1 and 2, and the stroke is just to clearly delineate this information.
Okay, so it doesn't refer to derivative differential, it's whatever comes out. The additional, I mean, the arguments after the stroke.
Yeah.
They don't necessarily refer to derivatives as they do before, but it's whatever comes out of the.
Yeah, exactly.
Right.
So we write it like this, and then I read it off. But this is how, I mean, what's happening in this duality is, here we have a metric, here we have a clear metric, and then we go, even now we have a momentum dependent function. But here we have a clear derivative of the metric, so we just call this the derivative of kinematic metric. It's just what in this duality language the covariant derivative of the metric is mapped to. Okay. So same goes for the Riemann tensor. That one is also now mapped to kinematic version of itself, which in Riemann coordinates given as we know, it's second derivative, it's a linear, it's a combination of second metric derivatives. So here B, A, B, O, and C, 1, 4, 2, B, 3, minus G, A, C, P, B, 1, 3, 4, plus C, the most bridging statement. Okay, so the recipe now for computing the kinematic Riemann tensor is we take our theory, we write down the action, the Fourier transform it, we read off the kinematic metric derivatives, we plug it in this formula. If you are in the normal coordinates, you have 3 points, you have more terms, you also have the observables, but then we have the Riemann, the kinematic Riemann tensor. And with that, now we have a very clean recipe, right? So we start with the functionality of the NLSM model. We perform a replacement, and we can get theories of arbitrary massless bosons by replacing kinematics, and replacing geometry with kinematics. The small price you have to pay is that sometimes locality can be lost. For example, or I mean, it's not lost, it's no longer that manifest. For example, here the curvature tensor phi to the 4 theory depends non-locally on some variables. This is kind of a relic of mapping other theories onto the NLSM finding numbers.
So this is for the 4-point. Is there a similar story for the higher points? No.
Yeah, I mean, well, as we replace with true false, we can take the 5-point NLSM amplitude, base the covariant derivatives of the tensor with its equivalent theory in this relative description. And yeah, this relative is really powerful. I mean, I checked on the scalar theories, right? We can apply to the 4 on the Goldstone. But you can also use this. It also works for gauge theory amplitude. So you can find a curvature tensor for Mills, for example, and perform the replacement of the NLSM, and you get the correct gauge theory amplitude.
Okay. And this works beyond tree level as well.
Yeah, this is what I'm gonna get to. It works beyond tree level until a very certain point before integration.
Okay.
So that's why I stressed so much the stuff that I probably just erased, this universal structure of the one loop amplitude. At this point, you can still replace it, and then you have to integrate and you get the correct result. You cannot take the one loop result of the NLSM after integration and then replace it. That's normal.
So at the level of the integrand, it will.
Exactly. Works on the integrand level. Okay, so now all the right tools in arsenal, let's go to what we call curvature renormalization. Okay. Let me restate it again. Then we have so far with our Lagrangian on half. Delta A B more 3 color, pure color renormalization. We just start the color superscript for emphasis. C B by C find D plus 1/4 G half A C B, which was C B. Okay. E find B. Okay. For that was a problem. Now through the geometry-kinematics duality, we can absorb this counter term, this higher derivative interaction into our.
I'm a little bit confused about indices now.
The second
The-
term.
Yeah, so
We're making less something or
also,
The CD seems to be contracted twice.
yeah,
The second term, ours.
no.
No, there, after the delta.
It means color, it means color.
yeah, sorry.
This is different type of index.
It means color.
Yes, sorry, that was supposed to. Yeah.
Oh,
I mean,
it just
sorry.
means color. Ah, okay.
No, I'm sorry, because we had a very subtle point where we misinterpreted it, so we made it very explicit in our paper. This is the ordinary, this one here, where we still have a nice interpretation of what we actually mean by the manifold. This is just a ordinary non-kinetic, non-running color.
It was col,
Yes.
C-O-L. Ah, I see.
Sorry. Okay, so you know the procedure now. We have the Lagrangian, we go to the action, we Fourier transform, and then we can read off on the the CD, which is now complemented the A, P, B, C, D, which is just A, C, E, D. Other Riemann tensor, the ordinary Riemann tensor of the NLSM plus 1/4 P A P B minus P P C G A B B C minus B C. Exchanging 3C and 4D. Sorry, maybe to avoid it explicitly because we just exchanged it. This part P C plus B D A C E. So that's now our new kinematic Riemann tensor that will takes care of this. That absorbs the counter term in a metric in our geometric picture. We can make sure that this works if we take the NLSM amplitude A, B, C, D, or A, B, C, D plus R, A, C, B, D, F. We perform our relative replacement by putting plugging it here. We can find the NLSM amplitude plus the term. It's S plus 1/4 S squared, which you have A, B, C, D, the other stuff, U squared, T squared, and so on. Okay, so this is actually the correct curvature tensor that we can plug into the duality to get the correct amplitude. Now, how can we see the running? So now we perform our renormalisation procedure. Renormalisation procedure where we redefine the coupling, so that G hat goes to Z, G hat delta G hat, where delta G hat A, B, C, D has to have the following structure to absorb the one-week divergence. Thank you for understanding. Epsilon R A M D R E M D M C D speed R A and then B C. Okay, so this counter term is able to absorb the one loop divergence of the NLSM. Now we solve the semantic equation to determine running. This one is given by the U, E, G, A, C, D, at over B, U, 2 epsilon, G, A, B, C, D,
What's the dimension of space time?
R. This is our NJ on the L. So A, C, D, and L. Okay, where G hat is obviously or is the coupling tensor of the higher of the counter term. Gij comma KL is just the derivative of the field space metric that will result in a colored Riemann tensor. Just found it simple to solve the equation with this. We can solve this equation, this differential equation for arbitrary G or for arbitrary R, but for our case, for this talk, let's just focus on the NLSM. R A B C D now given by minus lambda delta A B delta B C minus delta A C delta B D. With that one we can solve it. We can solve the Haslehner semantic equation for G hat A B C D, which we find running at B0 B, coupling at mu0, mu is 1, minus mu squared plus 6 squared, logarithm of mu times u delta AB delta BC delta AC delta E plus Q and 7. CD. Okay. So much back now this. We have a running of G. We can write down the RG and improve the Riemann tensor.
What is the N?
Sorry?
What is the N?
And
Re-
sorry, yes, exactly. N is the number of colors.
So UN or SUS?
Yes, exactly. So this space manifold in the NLSM, so ON and that N. More colors. Now with this we can write down our G tool. Riemann tensor. New, yes. Old color Riemann tensor of the NLSM plus A, B, B, G, at A, B. Sorry. Of mu minus C for D. Okay. And now to get a better understanding or intuition for what this means for the geometry situation, let's consider the Ricci scalar, which we obtain by setting all the momenta on shell.
Is there something different going on than you had on the? Why did the 1/4 vanish?
I'm sorry, it was a mistake. I was feeling to run a bit late. That's why I skipped the line. Sorry. No, but it's just, yeah, it's just this one, but now we have the addition of, now we don't have new G runs, so we have the new added. Now from this, we can contract the indices, set the momenta on shell, find the Ricci scale, equals a function ST, and the renormalisation scale, given by lambda, and minus 1 plus number over 6 pi squared, and n plus 2, over n minus 1, equal to smooth, minus minus 40 minus 1 u over the mean. Okay, so here we see clearly the tree level. At tree level, this is just the Ricci scalar of the n sphere with radius given by lambda to the minus 1/2. Here we introduce momentum dependence from the comforter. And here we see an additional running due to our renormalization procedure. So again, in a sketchy picture at tree level, we have here our sphere with radius 1 over square root lambda. At tree level, we want to go to loop level, our radius will change. Now our radius is now a function of the scattering kinematics and renormalization scale u, but it's still behaving like an n sphere. So some key takeaways here now of the geometry is momentum dependent and scalar dependent. The kinematic for the RD improves Riemann tensor RDCD. Still satisfies the structure T rho minus mu rho, so it still satisfies all the right symmetry, anti-symmetry properties, and geometry identities. And through this, you see how quantum kinetic corrections make the curvature run. And if you want to find manifold.
Can I ask a question at this point? So, what happens at large n?
Large n.
Yeah, because there seems to be like after appropriate rescaling a 1/n factor even at tree level, which we generally don't expect. Like there.
Sorry, what don't you expect tree level?
So, like if you appropriately scale lambda to absorb the leading n factors, so that you only have 1/n pieces remaining, which something that sometimes you generally do it for large n analysis, like Tooft-like large n analysis for like a large number of colors. So it seems that there might be a 1/n kind of piece even at tree level. You generally expect such suppressions to start from loop level, which is also there. My question is basically what happens at like large n is
Sorry, I haven't considered large n. Sorry, I don't think I fully
I think there is a column scaling that's just off. Like the first one goes like n squared, the second one goes like.
yeah, but there's also n into n minus one, right? So there might be.
The second term goes like n squared times n in cube, right?
Yeah, but if you rescale lambda by n square, and then you can see that there'll be a 1/n piece even at.
You might have same to scaling, right? You can go different scaling.
I see. Okay.
It's just a matter of that overall. That's the.
So okay, then there won't be any.
I think the unit company is the one that matters. That is still fine.
I see. Okay. Yeah. Okay. Okay.
Thanks. I think that's what it is.
No, I'm sorry. This is a general question. In this example, you took it for a sphere, but you said that you can solve it like for any arbitrary.
Yeah, exactly. But I particularly chose the NLSM because we have this nice interpretation of a sphere.
Yeah, of course.
Because I mean, we can do it, for example, for pi to the fourth theory, then we can find our mu will be something like lambda of mu over lambda of mu over t minus 4 over u. So there's no nice geometric manifold I can draw you for this topic.
Yeah. So, I mean, do you have any insight that if you have a manifold where the, let's say, the curvature tensor has different signs at different point, what happens under the normalization? This.
Okay, so that is a future direction we were thinking about investigating. I don't know if you know about positivity bounds in EFTs. So that one here is found to be positive.
Okay.
And since that one determines the corrections to the
I see.
curvature tensor, we could probably say something about this sign. But this positivity bound is just tree level. So at tree level, we know that G, A, B, C, D, or at least the linear combination thereof has to be bigger than 0. But at loop level, it's a bit more complicated. There we just know that it has to be bigger than, cannot go arbitrarily negative. Because yeah, that would be something that is interesting, that would be interesting to investigate. Because the no positivity bounds on this one here is can be whatever. But quantum corrections will probably tend to push it in a certain direction. Yeah, we've not worked it out yet.
And for this one, the renormalization is sort of pushing the sphere to grow to a bigger size. Is that the big
Yeah, that's really solid, right? So
is this sort of hinting that essentially this theory is flowing towards a free theory, like the FIFO theory is trivial non-contributive. Like if you keep pushing it and this geometry picture sustains, it goes on to a bigger and bigger sphere, which is like a flat space and there is no curvature.
yeah, I think you can see it that way. Thanks for the nice question and comments, please. That's just to recap the main points of this. Say it one more time. So we've given an interpretation to the kinematics dependent curvature and see how we effectively introduce a running. So interpretation for the AB at the function of the momentum. This is what we found today, and you've seen how we affect induce running the field space geometry. Particularly seen it a nice example of the rich scale where free level is just a constant, the loop level comes function of the scattering kinematics and the renormalisation scale. Okay, to get to this point, I mean, starting with a quick introduction of the field space geometry on the example of the NLSM, given it the Riemannian structure. And the Riemannian structure. We've linked physical observables with geometry of this manifold. And I've given you a brief introduction to the geometry-kinematics duality. And this is actually very useful when going to one loop. We observe, or I've given you or shown you the universal one loop amplitude structure. Just recap it here one more time. There you have momentum integral. A R A symmetries. Anti-symmetrized E. Symmetrized R B. B. Anti-symmetrized R C. B, where we now contrast, of course, the symmetrized and anti-symmetrized indices, and this is the point where we can still apply the geometry-kinematics duality. And apply the geometry-kinematics duality at this point. And for this result, we can already compute the one loop amplitude of arbitrary massless bosonic theories. So we can do phi to the 4, we can do potential, and do vector and tensor theories. Okay, and afterwards, I've shown you on the NLSM how to give a geometric interpretation to our Riemannian. Fractions. Okay. And with that, yeah, I want to conclude and thank you again for having me. And for questions that we have to discuss more.
Could this be done for supersymmetric field theories? We start with the supersymmetric nonlinear sigma model. The geometry is more constrained, so you have scalar geometry. And then could you learn something about Emil's theory in superspace or supersymmetric Emil's theory?
I mean, personally, I've not tried that, or we have not been working on the supersymmetric version, but I mean, so far with geometry-kinematics duality, they only worked it out for scalars. So they say there might be a generalization to include fermions, and that's why I think there might be an obstacle with going to supersymmetry, right? If you have symmetry that mixes I think you might have to first generalize it to fermions and then you can. So far, yeah, just scalar, non-supersymmetric symmetry theories.
But the kinematic color duality, I mean, that has been admitted to
Colour-kinematics.
Yeah,
Yeah,
that part is.
Yeah. Somehow, maybe you could argue that you know the theory is supersymmetric, and you know what the scalars are doing. So somehow the fermions have to behave. You know, they have to sort of
I see.
have to do the same thing, not to break supersymmetry because you know it's not broken.
yeah, I mean, I don't, as I said, I'm not sure about this. So. Christian doesn't mention it in his paper, to my knowledge. I mean, he seems like the guy who would have mentioned it if he had worked it out.
So are you thinking about fermions?
Yeah, that would be like as one of the possible future directions, right? So people are working on the field space geometry of the standard model, but they use a bit different approaches and they find of fermions. But yeah, so what we have to first figure out is how to include fermion in the geometry-kinematics duality picture, and then this would be extended fermions. Yeah, this is one of the possible future directions we could go.
I think with fermions it will be interesting in many ways because like fermions also have this coupling where the Riemann tensor itself appears. There's a coordinate fermion plane. So yeah. So I have a slightly different question. I mean, the potential case we can, as we discussed, we can handle with this geometry-kinematics duality. But one could perhaps take a different stance in the sense that any scalar with no mass but the potential, you can always rewrite it as a one extra scalar but a nonlinear sigma model. Like this, what is called this Eisenberg lift. Right. Okay. So the new NLSM is something with one extra scalar, and the metric of the target space would essentially be completely flat in most directions, except in the extra direction there is a sort of some dependence, and that dependence is basically controlled by the potential. So in some sense, that is another way of incorporating the potentials, and it might be interesting to see if this one says the same thing or not. So I don't know if it is just I don't know if you know this, like in point particle mechanics, there's this thing, I think Hertz, Henry Hertz was the first one who said that like any particle moving in a potential, you can think of it like moving in one dimension higher, which is carved in such a way and there is no potential. So it's called we call it forceless mechanics or something. It's just a field theory version of the same story. So any scalar theory with some parity term, no mass or the potential can be thought of as a theory of one extra scalar, but not like a sigma model no potential. So that might be an interesting thing as well.
Yeah, I mean, I must say, I've not heard of that, or we have not thought about that.
Yeah, sure. It's
Happy to read more about it later.
yeah, sure.
What happens if you are instantons?
Incident being like gauge instantons.
Yeah, I would naively expect some large structure in the field space geometry.
I mean, maybe we have not worked it out explicitly, but I mean, what this rests on is like, yeah, locally. Okay, locally we can go to RNC, so I don't know if you see some global stuff appearing, right?
It is within the realm of whatever should be able.
Yeah,
I mean, unless this is extended to see.
I'm assuming something like D-brain structure, but I don't know. I mean, the dictionary is not. That's why I was thinking addition of some large object in the field space geometry might correspond to something non-perturbative in the field theory.
What is the, I mean, how will, I mean, without appending that is set up in any way, I don't think it will be sensitive.
Just a nice question, like, is there any singularity-like structure in this story?
Singularity in terms of the
Curvature. Or like, article, there's a local, does it show up something, a singularity, something?
Not that we sort of know.
So I think manifold would be the situation where if the sphere was shrinking, and if all the sphere is kind of expanding, so that's why I said that it seems like you know it's going to. But maybe the intuity or something, there is some region to screen. Sorry, one more question. Massless scalars, of course, has a lot of nice IS structure. In particular, they have the soft theorems, right? The standard theorems and etc. Do you have any nice interpretation or connections in terms of the phase geometry or?
Yeah, I mean, there is a geometric version of this software.
Yeah, Leverton himself wrote this, right? Geometric soft theorems.
Yeah.
Yeah. So.
Yeah, exactly.
So.
It's Chan and Andreas Helset.
I see.
That's what also recently published a new version of this.
I think I missed that.
Was like 4 weeks ago now, so very recent.
Okay.
And then Tim Cohen. But yeah, that is yeah, I mean that is the geometric version of the Atlas theorem. The Atlas zeros movement, I would say.
But isn't there a lot of Python theory?
No, Wi-Fi theory is free. It's free here at the website. It's proven.
More questions? Thank the speaker again.